Hello class, this is Econ 510 Managerial Economics class. Today is March 24th, Thursday.
The class will review for the third midterm exam. Exam 3 covers chapter 7, 8, and 9 of your textbook. The topics are the short run and long run cost analysis in chapter 7, and market structure and competitive market in chapter 8, and monopoly market in chapter 9. So I'm going to pick a summary of each chapter for your exam review.
Suppose you have a business and you're producing something, maybe hamburgers, maybe television sets, and you'd like to know, how much should I produce so as to make the most profit I can from my operation? We're now entering a set of lectures that's going to equip you with the tools economists use for describing the behavior of profit-maximizing firms. In order to get to the question of what a profit-maximizing firm should do, we have to back up and start with some basics. The first thing we'll do is describe the technology of the firm. That is, what can the firm do with a given set of inputs to produce a certain amount of output? We're going to describe the technical or technological possibilities that a firm has for producing output from input. That is, for assembling television sets or making hamburgers. Once we have a description of the firm's technology, we will then look at the cost to the firm of producing output. What we do is we take the technology and combine that with knowledge of the prices that the firm has to pay for its inputs, like labor, raw materials, capital, and come up with the cost per unit of making hamburgers or televisions. Finally, we'll combine the information we have about the costs of production with information about the price at which the firm can sell its product. Once we've combined those pieces of information, we'll be able to predict the best course of action for a profit-maximizing firm. We'll be able to answer the question, how much output should a firm produce if it wants to maximize its profits, subject to its technology, the price it pays for its inputs, and the environment, the competitive environment in which it finds itself. So let's back off then of this big picture and focus on the first set of specific questions we'd like to ask. That is, what are the technological possibilities of a firm? That is, what can the firm do? We're looking now at a firm's technology, and a technology simply means a catalog of things that a firm knows how to do. What we're most interested in is how much output a firm can produce with a given amount of input. Now, this sounds a lot like engineering, doesn't it? It's because it is. Economics, when we describe production, begins with a purely engineering relationship. That is, a relationship that has nothing to do with economics and money and stuff like that, but has more to do with technological possibilities. What can the firm do, according to the laws of physics, according to its know-how, to turn labor and raw materials into its finished product? Now, we're going to start with a careful description of a firm's technological possibilities. And then we're going to look at how to represent those technological possibilities in a graph. Finally, we'll introduce some concepts that economists focus on when they describe the technology that a firm uses to produce its output. Let's start then with a chart that shows the technological possibilities that the firm faces. It's kind of like a production possibilities chart for the firm. And we call this production possibilities a total output relationship. Total output is defined as the total amount of output that a firm can produce using a given amount of input, subject to its technological know-how and any other factors that constrain its production. What a firm can do, given its know-how, with a certain amount of input. Total output, therefore, is the amount of output a firm can produce with a given amount of input. Let's look at the technological possibilities of a particular firm. Let's say this firm produces television sets. So their output in this case is TVs. And their input, let's say, is labor. Now, when we describe this relationship, total output, we're talking about what labor can produce, what a given amount of labor can produce in terms of television sets. But clearly, we need other inputs to make a television. We need raw materials, we need tools, we need a place to work. Whenever we describe the total output relationship in economics, we are usually talking about the short run. The short run is a period of time that is so short that you can only vary one or a few of your inputs. A plant that's producing televisions might decide over time that it wants to expand its operations, add another conveyor belt, get some more tools, build another warehouse. Well, you can do all that stuff in time, but in the short run, if you got a big order for television sets, you could only meet that big order by hiring more workers to come in and work with the factory as it exists now. The short run is a period of time during which some inputs are fixed and other inputs are variable. So when we describe the total output relationship, the first thing we want to do is to distinguish between fixed inputs and variable inputs. Let's suppose now that we are in the short run in our television production process. We're building TVs and suddenly we get an order to increase the number of televisions we're making. Maybe we get a big order from a department store. In the short run, let's suppose our only option for increasing output is to add more labor. Everything else is fixed in the short run. It's too expensive to alter quickly the number of conveyor belts, the size of the factory, the number of tools, and so on. So, for all practical purposes, our only variable when we're altering our output is labor, and we will call labor the variable input. Now, let me go back and define total output one more time. The total output of the variable input labor is the total amount of output that a given amount of labor can produce, holding constant technology, that is the firm's know-how, and holding constant the quantity of all of the other inputs that the firm uses, capital, the size of the factory, tools, anything else. We're going to consider those the fixed inputs. And whenever you write out a schedule like the one in front of me here, you're assuming that those fixed inputs remain fixed in the short run. So we've got a certain factory size, a certain number of conveyor belts, a certain pile of raw materials to work with. But in the short run, we can only produce more televisions by adding more labor. Let's look then at what the possibilities are in the short run. In the short run, if you have one worker, you can make 2 television sets per week. If you add a second worker with the same tools and the same technological know-how, you can make 10 television sets in a week. Employ a third worker, and the 3 of them can produce a total of 30 television sets in a week. 4 workers have a total product of 40 televisions per week. 5 workers will give you a total output of 45, and with 6 workers, you can make 48 television sets per week. As you see, as the numbers get larger, up to a point, the total output of labor increases. Oddly enough, if you go past a certain point, with 8 workers in this story, the total number of television sets actually drops by 1, from 49 to 48. This table of numbers, then, is a total output schedule. It shows you the total amount of output you can produce with given amounts of the variable input labor, holding constant technological know-how, and holding constant the amount of all other inputs used. The next thing I'd like to do is represent this information graphically. So, in the next lecture, we'll take this chart of numbers and put it into a picture. That picture will represent the production possibilities of the firm in the short run, and we will call that the total product curve. Remember, we're talking about how economists describe the productivity of a firm. Eventually, we're going to use this information when we prescribe what a firm should do to maximize its profits. But for now, we're concerned with the task of representing a firm's technology. Last time we looked at the total product curve, which tells us what a firm can do in the short run when it can vary only one of its inputs. We also described the marginal product of a firm. That is the additional output that the firm can produce by hiring an extra worker, an extra unit of the variable input. What I'd like to do now that we've discovered that marginal product is simply the slope of the total product curve, is I would like to draw a picture that puts the marginal product curve in a graph by itself. Let's look now at this diagram, and we've got another one of these now famous two-story diagrams. Remember, the trick with a two-story diagram is the graphs are related and they have the same variable measured on the horizontal axis. So in this case, we are measuring labor input on the horizontal axis in both pictures. On the upstairs picture, we're measuring total product on the vertical axis, and we're using those same numbers that we've been using all along to represent a total product, and those numbers are next door. In the graph below, we're going to now represent marginal product, and I've shown you those numbers. I calculated them before. It's the change in output that results from a change in the variable input, and these are my marginal product numbers. They're also next door as well. What I'm going to see is that when the curve is convex, that is, when the curve is increasing at an increasing rate, the marginal product will be increasing. That is, the slope is getting steeper, the marginal product is going to be increasing. When the slope is decreasing, that is, when the curve is concave, when total product is increasing at a decreasing rate, then the marginal product will be decreasing. This marginal product curve will be downward sloping. Finally, when the total product curve finally maxes out and heads south, that is, when extra workers actually decrease the total product of the operation, then the marginal product will itself be negative. So I've put the points from this diagram, from this chart. I put the points down here in the marginal product curve, and now I'm ready to connect them and draw the marginal product. So for one worker, the marginal product is 2. For the second worker, it's 10. For the third worker, it's 20, and so forth. So here is 2. Here's 10. I made a mistake there. I don't know why I had that point for 10, because I'm using this for 10 and this for 20. So there's 20. You know, you got to be careful about this. And that means when I go back to a marginal product of, oh, I know why, because that isn't a marginal product of 10, it's a marginal product of 8. Well, I got ahead of myself, so I can mark that point off. Here's what the curve looks like. 2, 8, 20, 10, 5, 3, 1, and -1. And hey, I'll save my mistake here by making it part of the picture. I'll use that as the letter P for my marginal product curve. Hey, there's a little lesson. Sometimes you can turn your mistakes into part of the art, and that's what I've done here. Now, the marginal product curve shows me the slope of the total product curve at every point. And by connecting the dots, you can see where the curve is convex, the marginal product is increasing. Where the curve is concave, the marginal product is decreasing. And where the curve goes negative, the marginal product is below 0. So this curve represents the slope of this curve at every point. I want to throw in two little points of information here that you might find useful. Sometimes we write total product with an L in parentheses afterwards to indicate that total product, that is the total output that you can produce in the short run, given your technology and given your amount of fixed inputs, is a function of labor. So we write this as a function of labor. I could also write marginal product also as a function of labor. I could write MP of L, because the marginal product changes as I add additional workers to my factory. The next thing that I want to point out is that we're talking here about the number of workers who are working in the factory at a particular time. It's not like you're hiring one worker or then a second worker later in the week or a third worker even later. We're talking about two workers working together for a week or three workers working together for a week. See, the change in the marginal product is part of the technology. There are things that two workers can do to produce televisions that one worker can't do by herself. There are things that three workers could do that two workers can't do. Teamwork and specialization become possible as you add extra workers working together at the same time. So when we talk about the marginal product of technology, we're talking about how productivity changes as you add additional workers that are working at the same time, at once, together, over a given period of time, like a week. Finally, the last thing that I want to point out is I've been using the term convex and concave. I sometimes forget which is which, so I'll show you a little trick, a little memory trick. A memory trick, by the way, is called a mnemonic device. Some of my students were telling me the other day I'd used the expression mnemonic device, and they started telling me that they liked these demonic devices. They thought they were helpful. So here's a little demonic device to help you. Let's suppose you're standing here on the axis looking up at a curve, and if you're looking up and you see a cave, then we say that the curve is concave. But if you look up and you're looking for a cave and what you see doesn't look like a cave, if it's bowed downwards and you're looking for a cave, well then you would be frustrated or vexed. So this is convex. So here is where you're vexed, and here is where you actually see a cave. If the curve is concave, you look up and see a cave. If it isn't, then you're vexed. The curve is convex. So now we've got a picture of the marginal product curve, which is the slope of the total product curve. And what we'll add next is another measure of productivity that you may often hear about in the newspaper, that is output per worker. And that's called the average product of labor. So we'll series of lectures that a lot of students consider very difficult. So we're going to take our time and try to do this extra clearly. We're going to be talking about the costs of production. Now, you'll recall we've just done a series of lectures on productivity, the firm's technology. Now we're going to talk about how you take the firm's technology, what they know how to do, and combine it with the cost of hiring inputs like labor and capital, and come up with the costs of producing output. In our case, the cost of producing television sets. This information is going to be very helpful to us when we move to the next phase, finding the profit maximizing output choice for a firm. So here we are, technology, costs, and profit. We're in the middle of this stream of questions that's going to lead us to the answer, what is the best choice for a firm to make if it wants to maximize its profits. Students find this material difficult because it involves a lot of different tools used at once. We're going to be looking at charts and some simple mathematics. Then we're going to be looking at curves that represent the information in those charts. So I'm going to try to do this very carefully. I'll show you some charts, then show you the curves that go along with it. And at each stage, I'll try to remind you of the intuition behind all of it. Let me start with what I think is a very simple explanation of the relationship between costs and productivity. The first relationship we want to begin with as we start our discussion of the costs of production is the relationship between costs and productivity. In particular, costs and productivity are inversely related. That is, when productivity is increasing, the cost of production is falling. And when the productivity of your workers is falling, the cost of production is increasing. Let me see if I can make that very, very clear. Let's suppose we have a television factory. And in this television factory, we have a certain number of fixed inputs, like the size of the factory, the number of conveyor belts, the number of tools. And we also have variable input, that is, the number of workers that we hire to assemble television sets. Let's suppose we start with an assumption about productivity. Let's suppose we assume right now that one worker, given her know-how and the tools available to her, can assemble 1/4 of a television in a day. If one worker can assemble 1/4 of a television in a day, then how many workers will it take to make a whole television? The answer is, it will take 4 workers. 4 workers, each assembling 1/4 of a television, will produce for us a whole television. Now notice the point that I'm making. If one worker has an average product or an average output of 1/4 of a television, 1/4, then the reciprocal of that, 4 workers, is what it takes to produce a single television set. Notice, productivity and costs are reciprocal. If one worker can produce 1/4 of a television, then it takes 4 workers to produce 1 television. And you've got to pay those workers the wage, and that's what determines the cost of getting that television put together. 1/4 is the reciprocal of 4. If 1/4 is the productivity of the worker, then 4 is the number of workers it takes, which becomes your cost of producing the television. This idea, this simple explanation, is the basis of the relationship between costs and productivity. The more productive your workers are, the fewer workers you will need to produce your output. Now what I'm going to do is I'm going to go step by step through a description of the different notions of cost of production. We will look at the costs associated with hiring labor. We'll look at the costs associated with having a factory and tools ready for those workers to use. And finally, we'll look at the cost of producing another television set. What is the cost on average of producing a single TV, and what is the cost to produce 1 extra television set? The notion of average cost and marginal cost. Along the way, after I give you an example of each of these concepts, I'll be taking a break and then drawing the curve that goes with each concept, so that when you look at the picture, you won't just see a line on the page. Perhaps you'll also see a story that relates productivity to costs. That way, when we finally come to the point of using these curves to describe the firm's profit-maximizing choice, maybe you'll have some intuition that makes this more than just a technical exercise. I hope so. So we'll move now to the first concept of cost, and that is the cost of hiring the labor to produce your output, the variable cost of production. Out here to do a little trick to show you the relationship between productivity and costs. I want to recall a diagram that we spent a lot of time developing a little while ago. That was the total product curve. Remember, the total product curve shows you the relationship between the amount of labor your firm hires and the number of television sets you produce in a week. For instance, if you hire 2 workers, you'll be able to produce, according to the numbers we've been using, you'll be able to produce 10 television sets a week. If you hire 3 workers, then you'll be able to produce 30 television sets a week. That's your productivity. Now, think about this diagram viewed from the other direction. Suppose you ask yourself, how much will it cost my firm to produce 2 television sets? Sorry, so how much will it cost my firm to produce 10 television sets in a week? So instead of starting on the horizontal axis and going up to the total product curve, we're starting on the vertical axis and going over to the curve. We're saying, if we want to produce 10 television sets a week, how much are we going to have to hire, how much labor will we have to hire to make that happen? And the answer is, we're going to have to hire 2 workers. If we want to, however, increase our output up to 30 television sets a week, going over to the curve, we're going to have to hire 3 workers. Now think about this for a minute. Once you know how many workers you have to hire, you know how much it's going to cost you in labor expense. Remember, those 2 workers cost you $1,000 each for a total of $2,000. If you want to make 30 television sets a week, you've got to hire 3 workers. That's going to cost you 3 times $1,000 or $3,000 a week. The point I'm making here is that you can use the information in the total product curve to derive your costs. Only you're just reading the curve in a different way. Rather than starting with the number of workers and finding their product, you're starting with the product you want to produce and figuring out the number of workers that you'll need. This is exactly the information that we're looking for when we draw the variable cost curve. Only the axes are reversed. Instead of putting product on the vertical axis and labor on the horizontal axis, the way we do in our product curve, we flip things around. We put the total amount of output on the horizontal axis, and not just labor, but its cost on the vertical axis. Let me show you how to turn a product curve into a cost curve. Start with our product curve, and the first thing you want to do is flip the axes around. So I'm going to pick up my product curve like this. I'm going to pick it up and flip it over and lay it right here on my cost graph. Notice what I have now is a kind of inverse or mirror image of my original curve. Now, if I want to produce 10 television sets in a week, I know that I have to hire 2 workers, and I multiply those 2 workers by $1,000, and I'll get my variable cost. So in order to turn a product curve into a cost curve, you need 2 steps of geometry. The first step is take your product curve and reverse the axes, taking the curve with it. So we've just flipped the curve over and put the axes, the horizontal axis on the vertical and the vertical axis on the horizontal. The second step is you take this curve and you stretch it upwards by multiplying it by the wage. Each of these points represents a number of workers that you'll need. Now multiply that by $1,000 a week and it becomes your labor bill. So what I do is I take this curve and stretch it upwards and I get the variable cost curve that I drew a moment ago. And it looks like this. Notice this variable cost curve has the same shape as my inverted total product curve. It's just stretched upwards because I multiplied all of these numbers by the wage of $1,000. Now that's kind of a cool little trick. And if you want to try this trick at home, you're welcome to. I always like to draw my total product curve and then hold it up to the light, look at it through my paper and see its inverse. It's a neat way, a neat geometrical way of making it clear to you that cost and productivity are inversely or reciprocally related. It's because we're changing the axes and stretching the curve. There's the relationship. In the last lectures, we discussed the first problem that the firm faces in the long run. That's the problem of choosing the cost-minimizing technique, the way of combining capital and labor so as to minimize the cost of producing a given quantity of output. In this lecture, we're going to consider the second problem that the firm faces in the long run, and that is the choice of the optimal scale, the right size of operation for maximizing your profits. In the short run, the firm can't help but change its scale and change its technique at the same time. If the firm wants to produce more output in the short run, they've got a fixed amount of capital, and they can only increase output by adding more labor. That means that in order to increase the size of their operation or their output of television sets, they've got to add more workers, which increases the intensity of labor. That is, we're using more labor per unit of capital. So they're also choosing scale, the size of their operation, at the same time as they're choosing the technique of production. 3 workers and 1 tool may be the only option that's available to the firm for increasing their output in the short run. The firm is simultaneously choosing the technique of production and the size of their operation. In the long run, the firm gets to choose these 2 things separately, which is one of the reasons why long-run costs of production are always lower than the short-run costs. The firm has more flexibility. If the firm wants to increase the size of its operation, it doesn't necessarily have to use more labor per unit of capital. It can also increase the amount of capital that each worker has, thereby keeping the labor-capital ratio constant even as its firm grows bigger. That is, it keeps the cost-minimizing technique that it prefers while allowing the scale of operation to grow larger. The definition of the scale of operation is as follows. Scale is said to increase if the firm has a proportional increase in all of its inputs. So if we start with 1 worker and 1 unit of capital, the scale of the firm is said to increase if we add a 2nd worker with a tool of his own, and a 3rd worker with a tool of her own. To have an increase in the scale, it is required that all inputs increase by a particular proportion, that they all increase by the same proportion. If we just increase labor and hold capital constant, that is not a change in scale. If we just increase capital and hold labor constant, that is not a change in scale. To change the scale of operation, you must have a proportional increase in all of the factors of production. Now, here's the question that we want to answer. How does the firm's productivity change as we change the scale of operation? In order to answer that question, we're going to need to define a concept very specifically, and that's the concept of economy of scale. What happens to the firm's productivity when the scale of its operation changes? Suppose we go from 1 worker with 1 unit of capital to 2 workers and 2 units of capital. What happens to output? Well, you can imagine that one of 3 things would happen. The first is probably the most reasonable assumption, and that is that if both of our inputs double, our output would double as well. This is the case when the firm is said to have constant returns to scale. Constant returns to scale is defined as a technology where increasing all inputs by a given proportion increases output by the same proportion. The reason this seems like a reasonable assumption is the possibility of replication. If we've got a guy over here making television sets by using a particular tool, and he can make 10 television sets a day, if we have another worker who has the same toolkit, we would imagine that that worker could also make 10 television sets a day. Replicating this operation would allow us to double the amount of output we get in a single day from our factory. If we had a 3rd worker also with a tool, we should be able to replicate the operation again. Tripling inputs, we would expect to be able to triple output. That is the idea of constant returns to scale. And it seems like a reasonable assumption because of the possibility of replication, having someone else do what another worker with his tools is already doing successfully. Now, there are 2 other possibilities. The first is the possibility that things are actually better than constant returns to scale, that adding a worker with a tool adding a second worker with a second tool allows us to more than double our output. That is, if we have one worker with one tool producing 10 television sets, two workers with two tools might actually be able to produce 30 television sets in a day. That would be the case if somehow there's some kind of teamwork and specialization between these workers. If working together, they can operate in a way that's more productive than if both of them work separately. Having the workers work together and cooperate, using their labor and tools together, may actually allow them to be more productive than two workers simply replicating what each other are doing. This is the case with increasing returns to scale. The final possibility is the possibility of decreasing returns to scale. It may be that by doubling all of our inputs, we actually increase output by a smaller proportion, maybe only 10% or 20%. Now, you might ask yourself, why would we ever have decreasing returns to scale? What could ever lead to a situation where two workers with two tools would do less productive work than they could do if they were working separately? And it has to do with the problem of a growing organization. As an organization gets larger and larger, you have more and more activity under a single manager. And that manager is responsible for making decisions about how this process is organized, how the workers are paid, how they are scheduled, how their activities are coordinated. When you've got a manager who's over this whole operation, it may be that the individual workers say to themselves, hey, rather than trying to make my money by working harder producing television sets, I'll go and lobby the manager for a raise. I'll go and ask for favors. I'll ask for a better schedule. I'll try to use my influence to improve my position in this organization. This is a form of rent-seeking, and it goes under the name of influence activities. Influence activities are efforts on the part of the workers to influence the organization to their advantage. And the cost of these influence activities is this. When workers believe that they can get more benefits by lobbying the boss, they'll spend less time actually producing televisions for the firm. Because of that, as the organization grows larger and the manager has more and more power, it is a greater and greater temptation for the individual workers to engage in influence activities rather than to produce television sets. And the cost of production then goes up as the firm has to employ monitors to make sure that people stay on the job and don't spend their time taking too many breaks, going and lobbying the boss, and such things like that. This is the idea behind decreasing returns to scale. As the firm gets very large, the problem becomes managing workers and preventing them from engaging in influence activities. So, this is the idea of scale economies. The firm wants to consider, what is the potential for teamwork and specialization? What is our scope for enjoying increasing returns to scale? Because as long as we're enjoying increasing returns to scale, it will probably pay for us to expand our operation. Also, we want to know, when are we likely to have constant returns to scale? Because anytime a firm has constant returns to scale, replication is a possibility. And finally, there's the problem of decreasing returns to scale. If the firm grows too large, its workers are tempted to engage in influence activities, thus raising the cost of production. In the next lecture, we'll see how economies of scale translate into the costs of the firm in the long run. We're ready to talk about the profit-maximizing strategy of a firm. But before we get into the details, we need to make one thing very clear. The definition of profit is total revenue minus total cost. And total revenue, that is, the revenue that a firm earns from selling its product, is equal to the price of the product times the quantity that the firm sells. Now, here's what we need to make clear. Does the firm have the power to set its own price, or is the price given to it by the market? That is the firm a price taker or a price maker? Are they a firm that accepts the prices given, or does this firm have the power, by altering the amount of output that it produces, to manipulate its price? Later in this series, we're going to look at the decision that faces a firm that has the power to set price. We call that power market power. A firm that can influence the price of its product by changing the amount of output that it sells is a firm that is said to have market power. And an extreme example of market power is the monopolist. However, right now, to make the problem very simple, we're going to look at the other extreme. A firm that has no market power. A firm that takes prices as given. When a firm is unable to influence the price of its product, when a firm takes as given the price of its product that's set by supply and demand in the market, we call that firm competitive. The term competitive in economic theory refers to the behavior of a firm that cannot influence prices, the behavior of a firm or of any agent that must take prices as given. So in all of the analysis that we're about to do, all of our discussion of profit maximization, we're going to assume that we're dealing with a competitive firm. As far as our television factory is concerned, it cannot set the price of its televisions. The price at which it can sell its televisions is given to it by the market. Supply and demand out there in the big market determines that you can sell a television set for, say, $500. And if our firm wants to sell televisions at $500 a piece, we will imagine that they can sell as many as they can produce. If they try to charge $501, they will not be able to sell any televisions because competition will drive them out of business. On the other hand, why should they sell their television at $499 when they can sell all they want to at $500? If the firm is competitive, that is, if the price is set in the market and our firm is small enough so that its actions don't influence the market price, then the firm will always charge the market price for its product. It won't charge more because it will lose all of its customers. It won't charge less because then it would be giving up revenue that it doesn't have to give up. It will always charge the competitive price. So keep in mind now, as we launch into our discussions of profit maximization, that for the time being, we're dealing with a competitive firm. A firm that takes the price of its product and the price of all of its inputs as given. No matter how much output our television factory produces, it is unable to influence the market price. Imagine you're running a television factory and you want to make maximum profits. You're trying to decide how many television sets to produce. What rule are you going to use to decide whether to produce one more television set? The answer is, you'll produce an extra television set anytime that extra set adds more to your company's revenue than it adds to its costs. You're never going to produce a television set that costs you more at the margin than the revenue that it adds. That would be subtracting from your profits. But the rule of producing up to the point at which marginal cost is just equal to the price, that's the rule that a competitive firm uses to maximize its profits. Let's look at how that rule looks in a graph. We're dealing with a firm in the short run that's trying to maximize its profits. And we've made a particular assumption about that firm. We've assumed that it is a competitive firm. Now, I haven't used this term before, but now is a good time to introduce it. A competitive firm is a firm that can take any action it wants to. It can produce as many television sets as it chooses to without influencing the price of its product. A competitive firm is a firm that can take any action without having an effect on the price of its product. Therefore, the price of your product is a given, a constant, something determined in the market that you have no control over. We've imagined that our competitive firm, in this example, can produce televisions at a price of $500 per television sold. That is, the price is constant at $500, no matter how many televisions you produce and sell. If that's true, will you produce another television set if you want to maximize your profits? The answer is, it depends on the cost of producing that television set. The cost of producing an extra television set is called the marginal cost of producing that set. The marginal cost of production, if it's less than the price, signals you to produce the television set and thereby increase your profits. But if the marginal cost is greater than the price, producing that television set would actually reduce your profits, and therefore it's not something you should do. Let's look now at this story in a picture. Here's a picture that you're familiar with from our last discussion. The total revenue curve is a straight line away from the origin, which represents the situation of a competitive firm. You can produce all the television sets you want to and sell them at a constant price of $500 apiece. The total cost curve now has a shape that reflects the productivity of the firm. First, you have diminishing marginal cost as marginal product increases due to teamwork and specialization. And then you have increasing marginal cost as congestion of the fixed inputs occurs. We now want to represent this picture, the same information, in this graph below. I'm using another one of my double-decker graphs, which means I have to be clear that on the horizontal axis I'm measuring the same thing. In this case, I'm measuring output on both of these axes, and I'm using exactly the same scale. Now, the first line that I'm going to draw in the diagram below is the firm's marginal revenue. Marginal revenue is defined as the change in total revenue that results from a change in output. Now, how does marginal revenue change? How does the firm's total revenue earned change if it sells one more television set? The answer is, it changes by $500, the price of the television set. It doesn't matter whether it's your first television sold, your 10th, or your 100th. Each television sold will always add $500 to your total revenue. $500 is the marginal revenue, which in this case, the case of a competitive firm, is equal to the price of a television set. A quick note, for a competitive firm that cannot influence the price of its good, marginal revenue is always equal to the price of the product. So let me draw in a line that represents marginal revenue. In this case, marginal revenue is the price of a television set. And price of the television set will always be equal to $500. So here I have a line with a slope of 0. It represents a constant, and this line is representing the price of a television set. In my story, that's $500. Now, let's represent next the marginal cost of producing a television set. Where do I get information from this picture on marginal cost? Where in this picture do I see the marginal cost of production? The answer is, it is the slope of the total cost curve. Remember, marginal cost is defined as the change in total cost that results from a change in output. It's the rise over the run, the slope of the total cost curve. So I want to graph a picture of the total cost curve, and let me see where the inflection point is. It looks like the inflection point might be right about here. This is the point where the total cost curve is no longer concave and becomes convex. That is, the slope stops decreasing and starts increasing instead. So if this is my point of inflection, this will be the point at which marginal cost is at a minimum. The slope has decreased and decreased and decreased and decreased, and it's just not going to get any lower. So here's the point of minimum marginal cost. Now, two other points that I want to notice. First of all, this point right here, this output level, in our last lecture we called this output level Y star. This is an output level at which the slope of the total cost curve is the same as the slope of the total revenue curve. This is an output level at which price is equal to marginal cost. So marginal cost at this point will be equal to price. And I can call this point Y star, just like I did before. That's Y star. Over here is another point where the slope of the total cost curve is equal to the slope of the total revenue curve. And this point before I called it Y dagger. Y dagger is another point where marginal cost is equal to price. Y dagger. That's the point at which losses are maximized, by the way. All right, now, if I keep the marginal cost diminishing until I reach the inflection point, and then have it rise after that, I will be drawing the slope of the total cost curve in this downstairs graph. So let me do that. Here's diminishing marginal cost, bam. Then marginal cost increases, bam. And there's your marginal cost curve. Again, what have I drawn here? This marginal cost curve is simply the slope of the total cost curve at every point. And I had some points that I knew had to be on the curve. The point of inflection, where marginal cost is at a minimum, and these 2 points where marginal cost is equal to price, Y dagger and Y star. Now, I can use this diagram down below to make an intuitive point about profit maximization. I argued before that this point, Y star, was the point of maximum profit for the firm. How do I know that? Well, if I look in the upstairs diagram, I know that because that's the point where the gap between total revenue and total cost is the biggest. That's the point where profit is maximized. But downstairs, I can tell the story a different way, using a different intuition. Let's suppose now that you run that television factory, and you're producing at this point Y star. Is that a good point for you to be at? The answer is yes. If you increase your output beyond Y star, what's happening? You're adding $500 for that television. If you produce another television at that point, you're adding $500 to your revenue. But the amount that you're adding to your costs is greater. What does that mean? It means that that next television is actually shrinking your profits because it costs more to produce than it earns you in revenue. So you don't want to go past the point Y star. You also, however, don't want to decrease your output. If you decreased your output, you would lose $500 by not selling a television set. If you back off and produce one less television set, you're going to cost your firm $500 in lost revenue. How much are you saving on the labor that you're not employing? Well, notice the savings is less than $500. The savings is less than $500. So you're sacrificing $500 in lost revenue, but you're only saving yourself maybe $450 in costs that you don't incur. It's not worth it to save $450 if it means you're throwing away a $500 sale. Therefore, you don't want to move backwards from that point either. If you're at this point Y star, where price is equal to marginal cost, you do not want to produce an extra television set. You also do not want to produce one fewer television sets. This is the point that is unimprovable. This is the point at which profit is maximized. Suppose we were back here at another point. Let's say this point of inflection. Just pick it, for example. Is this a good place for your firm to operate? The answer is no. How do I know? How could you improve your situation if you were at this point, if you were producing this smaller quantity of television sets? How could you improve the situation? You could produce more television sets. If you produce more television sets, notice, each television set that you produce adds how much to your revenue? $500, the price of the television set. Each one of them costs how much to produce? Well, some amount less than 500. Notice the green line is below the blue line at that point. If marginal cost is less than marginal revenue, if marginal cost is below the price of the good for a competitive firm, you can always increase your profits by increasing your output. As long as the cost is less than the price, by all means, make more television sets, drive up your profits. If you're over in this region and producing a large quantity of television sets and the marginal cost is greater than the price, By all means, back off. Produce fewer television sets, because the money that you save by not producing those television sets, the money you save by not employing the extra workers, is greater than the money you lose on the lost sales. You economize more by not hiring the workers than you would lose by not producing the televisions. So back off. Save more than you lose in revenue. Save more by economizing on costs. It's only at the point where marginal cost equals price. It's only at this point that the firm cannot improve its situation. Now, one final note. Look over here at Y-Dagger. Y-Dagger is another point where price is equal to marginal cost. Y-Dagger, on the other hand, is a bad point, because anything you do, any movement away from Y-Dagger makes you better off. If you're at Y-Dagger and you increase your output, what happens? Well, look, you're adding television sets that earn $500 apiece, and the cost is less than $500. Get away from Y-Dagger, increase your output, because price is greater than cost. As you increase your sales, that's going to add to your profits. The televisions are bringing more in revenue than they cost to produce. Look, even if you reduce your output, you're improving your situation. Because if you back off here, each of those televisions is bringing in $500, but they're costing more to produce at the margin. So if you reduce your output away from Y-Dagger, then you're saving more in labor costs than you're losing in lost sales. Y-Dagger is an awful point. In fact, if you look at the picture, you can see it's the worst you could possibly do. It's the point of minimum profit, the point where cost is the highest above revenue that it ever gets. So, let me summarize. The point at which profit is maximized is the point where price is equal to the marginal cost of production. This is the rule for profit maximization for a competitive firm. Any competitive firm, to maximize its profits, must be producing at the point where price equals marginal cost. There's one additional condition, and that is, it's not enough to be at the point where price equals marginal cost. You also have to be at a point where the marginal cost curve is sloping upwards. That is, you have to be at a point where marginal cost is increasing. That's what distinguishes Y-star from Y-dagger. Y-dagger, where marginal cost is decreasing, is a terrible point. It's the point of minimum profit. Y-star, where marginal cost is increasing, is actually the point of profit maximization. So our two conditions are, first, price equals marginal cost, and next, that the marginal cost curve itself must be upward sloping at that point. Marginal cost must be increasing. If those two conditions are satisfied, then the firm is maximizing its profit in the short run. Just because a firm is maximizing its profits doesn't mean it's actually making a profit. It could be minimizing its losses instead. How do we show the total profit that a firm earns when it's doing the best it can? I'll use now the graphs that we've developed, the cost curves, and use them in conjunction with the price of the product to show you what profit maximization looks like when the firm is earning a profit and what it looks like when the firm is making a loss. Let's start with a fortunate firm that's making a profit. Now, what is profit? Profit is the difference between total revenue and total cost. And the profit per unit that a firm earns is the difference between the revenue per unit, which is equal to its price, and the cost per unit, which is equal to average total cost. Let's look now at the diagram and bring those concepts into clearer focus. We'll start with the cost curves that we developed in the last series of lectures. Here's the marginal cost curve that tells us the cost of producing an additional television set. Here's the average total cost curve that tells us the total cost per unit of producing television sets. And notice that varies as labor productivity varies. Here's the average variable cost curve that tells us the labor cost per television produced. Once again, varying as labor productivity varies. And the difference between the average total cost curve and the average variable cost curve, what is that? It's the average fixed cost. Average variable cost plus average fixed cost equals average total cost. And why is it that the average total cost curve and the average variable cost curve get closer and closer as output increases? It's because average fixed cost is headed towards zero as we spread the fixed cost out over more and more units of output. Now, let's see what's going on in this firm. Let's suppose we have the price of the product. In our example, we've been looking at television sets that sell for $500 a piece. We have a competitive firm here that can produce as many televisions as it wants to and sell them at $500 a piece. It's competitive, which means that it cannot influence the price of its product. Whether it produces a lot or a little, it can still sell its televisions for $500 a piece. Now, if the price is $500, how many television sets will this firm produce if it wants to maximize its profit? Let me give you a chance to answer that question. Where in this graph will the firm be operating if the price is here and the firm wants to maximize? The answer is, take the price and go over to the marginal cost curve. Remember, the rule for maximizing profit for a competitive firm is the firm produces up to the point at which marginal cost equals price. Don't go past that point, or your costs will be greater than revenue for each additional television set. If it costs more to produce the television than you can make by selling it, then you're cutting into your profits. But don't stop shy of that point. If you stop short, then you're giving up profit because the revenue on those televisions is greater than the cost of producing them. Keep producing up to the point at which price equals marginal cost. That will maximize your profits. That means our firm wants to produce an output, and we'll call this output Y star. That's what we've been calling it all along, the output that maximizes profits. Now, we've got a firm here that's doing the best it can. A firm is always going to produce where price equals marginal cost and the marginal cost is increasing. That's the best a firm can do. That's the point of profit maximization. Now, however, we're going to ask ourselves, when this firm is doing the best it can, well, how well is it actually doing? Is it making a profit? Is it making a loss? What? How is this firm doing? Well, in order to answer this question, let's again think about profit. Profit is total revenue minus total costs. If you look at the picture that we've drawn here, you can actually see the firm's total revenue. Where is it in this picture? Where in this graph can you see the firm's total revenue? Remember the definition of total revenue, price times quantity. Total revenue is seen in this picture as the area of this rectangle. The height of the rectangle is the price the firm charges for its product, and the width of the rectangle, or the base, is the quantity that the firm produces. Price times quantity gives you the area of this rectangle that I've drawn here as a black box with dotted lines here and the axes as the lines on this side. This rectangle right here is the firm's total revenue from selling this quantity of televisions at this price per unit. Think of this as a big chunk of money that the firm takes in. Now, here's the question. What does the firm do with the money? Who gets it? Who is entitled to the revenue that the firm takes in from its sales? Well, let's look at the diagram here. The first thing we notice, if we look at this quantity Y star, let's imagine that this is 48 television sets. If the firm is producing 48 television sets, we can go up from 48 television sets. We can go up from Y star and find this point on the average variable cost curve. What does this point tell us? If we follow this point over to the axis, it gives us a dollar value. The question I'm asking you to answer is this. What does that dollar value tell us? 48 television sets. Here's a point on the average variable cost curve. What is this amount of money on this axis going to tell you? It tells you the labor cost per television produced. It tells you how much you have to pay your workers for each television they produce. Now, if you take the average variable cost, the labor cost per unit produced, and you multiply it by the number of units that are produced, what do you get? You get the variable cost, the total money that you're spending in your firm to pay your workers who are making your 48 television sets. So, if we multiply the number of units that are produced, the base of this rectangle, times the average variable cost, that is the labor unit per television, multiply that by 48 televisions, and this little area down here at the bottom is the firm's variable cost. Now, you can think about this as kind of a parfait, one of those desserts that has lots of different layers. The bottom layer of our parfait is the variable cost, the amount of money that the firm has to pay its workers who are producing the 48 television sets. So if I want to, and I do want to, I can label this particular chunk of the parfait with a VC. This chunk down here at the bottom, and I could shade in the whole thing, but I don't want to make my graph too cluttered. This whole bottom chunk of the parfait is what's going to the workers. This is the chunk of total revenue that goes to the workers to pay them for their labor. Now, if we follow our 48 television sets further up, we hit another curve. The next curve that we run into is the average total cost curve. So if we follow this dot over to an amount of money on the axis, what's it going to tell us? We're producing 48 television sets, and this is the point that we touch on the average total cost curve. What does this amount of money tell us? It tells us the average total cost per television produced. That includes all the workers as well as all the capital we're using, tools, factory space, resources, everything else, all those costs that are fixed in the short run. So this little chunk of the parfait now that's sitting on top of variable costs, what is that? That's average total costs after you take out the variable cost. Well, what's left? What's the difference between total cost and variable cost? The answer is fixed cost. The difference between the average total cost curve and the average variable cost curve at every point is the average fixed cost. If you multiply this average fixed cost times those 48 television sets, times the number of units that you're producing, what do you get? Well, average fixed cost times the number of televisions you're producing is just fixed cost, the total fixed cost. Let's put fixed cost now in this picture. And I could shade in this whole area, but again, I don't want to confuse the diagram. So this whole area right here, the second layer of the parfait, is the fixed costs. All right, quick review. We've got this big black rectangle which represents the firm's total revenue, price times quantity. We went up to the average variable cost curve and identified average variable cost when we're producing 48 televisions. We multiplied that by our 48 televisions and we got variable cost, the total wage bill that this factory has to pay. That comes out of their revenue. Next, we looked at the difference between average total cost and average variable cost, and what's left over is the average fixed cost. We multiplied that by our 48 television sets, and that gave us the fixed cost of production. Now, if we add fixed cost and variable cost together, what do we get? We get the total cost of production. And if we subtract the total cost of production, these two bottom layers of the parfait, if we subtract them from the big black rectangle, what's left? What's total revenue minus total cost? The answer is, it's the profit of the firm. That is, the layer that's left on top. After we've subtracted fixed and variable cost, the layer that's left on top is the firm's profit. And I'll use the symbol pi to indicate that. So, by way of review, here's the way we examined the firm's profit-maximizing decision and their profit position. First, we took the price of their good. They're a competitive firm, they take the price as given. We then let the firm maximize profit by continuing to produce until marginal cost was equal to price. That gave us Y star. Y star is the profit maximizing output of this competitive firm. Notice it's where price equals marginal cost, and it's where the marginal cost curve is sloping upward. This is the best that our firm can do. Then we broke down total revenue into some chunks. First, we found average variable cost using the ABC curve and multiplied it by output to get the bottom chunk of our parfait. This is the chunk that goes to the workers. Then we found the difference between average total cost and average variable cost. That's average fixed cost. We multiplied that by our 48 television sets and got the fixed cost. What's left over is the difference between total revenue and total cost. And that is, by definition, the profit of the firm. Now, I'm going to do the same set of steps, the same analysis on a different firm. This firm is not going to be as fortunate because it's going to turn out that they are in fact not making an economic profit in the short run. They'll be making a loss. Let's examine now a different situation. Suppose you're a firm that has a highly desirable product and you're the only one who offers it. How would you price your product? How much would you sell? The more you sell, the lower the price will be, according to the law of demand. But the higher you raise your price, the less of the product people will buy. How do you, as a firm who has market power, make the decision about how to price your product? We're going to be studying this problem in the coming lessons, and we will begin this lecture by introducing the concept of market power and talking about an extreme case, the case of a single seller, a monopoly. Let me begin by defining market power. A firm is said to have market power if it is able to influence the market price of its good or service. That is, if it has the power to set a price for its product rather than take the price as given in the market. Market power is a contrast to a competitive firm. A firm that is competitive is a price taker. A firm with market power has the ability then to set its price. An extreme case of a firm with market power is a monopolist. A monopoly is a single seller of a good or service. Now, you may be hard-pressed to come up with an idea quickly of a firm that really exists in the real world that's a true monopoly. In fact, monopolies are quite rare. And monopolies usually arise due to one of three factors. The first factor that can create a monopoly is a firm that has sole ownership of a particular resource that is important in the production of a good or service. An example of this would be the case of the market for diamonds. There was a time when the De Beers diamond cartel owned almost 80% of the world's diamonds. Many of the competitive diamonds were in the Soviet Union and were not available on the market at the time. Because one single company owned so many of the diamond mines, they were able to have considerable influence over the price that was charged for diamonds. So one thing that can create a monopoly is if a company has sole ownership of a particular resource that is important in the production of the good. Another example would be if we were at an airport, for example, and one company had sole ownership over the space that was available for selling concessions. If they owned that space, they then would be the only restaurant in the airport and would therefore be a monopoly. This brings us to the second situation that can create a monopoly, and this is monopoly that is created by government action. Government action meaning patents, copyrights, and in some cases, special licenses. In these cases, the government creates a situation whereby entry into an industry is prohibited. For example, one of the important driving forces in the pharmaceutical market is companies' desire to obtain a patent for a new effective drug to treat a certain kind of illness or condition. The company that develops the new drug first will be granted a patent, and with this patent they will have the sole right to produce and sell this drug in the United States for a period usually as long as 14 years. In this case, a drug patent grants a monopoly to a company, allowing it to have sole right to sell this product. And because there are no competitors, at least while the patent is in effect, unless the company wants to license production to other companies, while this company has the patent, they have the right to be a monopolist. And being a monopolist allows them to earn extra profit and thereby recover the costs that they sank into developing this new drug. Other things that can give companies patents granted by the government, or other things that can give companies monopolies granted by the government, are called sole licenses. It has been the case throughout history that governments have granted single licenses to particular companies to provide particular types of service. For example, the Hudson Bay Company, which was a licensed by the King of England to develop trade in the New World, had a monopoly right to on behalf of England, go and provide imports and exports to the New World. A third case in which we get a monopoly is what we call a natural monopoly. A natural monopoly arises because of the interaction between the size of the market and the efficient scale of operation of a single firm. Let's look at a picture that will make the idea of natural monopoly a little clearer. You'll recall from our earlier discussions that the bottom point of the long-run average cost curve determines the efficient scale of operation, or the right size for a firm in the long run in this market. Firms that want to be competitive in the long run will be operating at the bottom of their long-run average cost. That is, they will be minimizing the average cost of production and thereby maximizing their profits. If it's a competitive market, firms will continue to enter until the price of the good drops down to the bottom of the average cost curve. Now, if the long-run average cost curve is relatively close to the axis, that is, if the long-run average cost curve points to a point of efficient scale that is small relative to the amount of the product that the market wants to buy. That is, if the demand curve is way out here and the point of efficient scale is way back here, then there's room for a lot of other firms to enter this market. We'll get several of these blue curves fitting in, adding up to the total amount of the product that the market is actually buying. That is, if the efficient scale of operation is small relative to the size of the market, it takes a lot of firms to meet demand at this minimum average cost. However, if scale economies are very great, if the economies of scale are large relative to the size of the market, then we can get a situation like this, where the long-run average cost curve reaches its minimum point at a point that might be actually beyond its intersection with the demand curve. In this case, it only takes one firm to meet the entire market's demand for this product at minimum average cost. If we look at the point here of minimum average cost, it's beyond the demand curve. This firm can produce everything that the market wants to buy at a price equal to minimum average cost. This is a case when an industry has very, very great economies of scale, where the opportunities for teamwork and specialization, increasing returns to scale, and diminishing average cost go on for a long time. That is, the economy or the industry grows very, very large before it runs into problems with management and communication and all of those other things that lead to decreasing returns to scale. When the economy has a lot of scale economies, when the firm has a lot of scale economies relative to the amount of the good that people want to buy, then we have what we call a natural monopoly. When the point of efficient scale is enough to provide all of the good that the market wants to buy from a single firm producing it, then we have a situation of natural monopoly. Some examples of this that have been cited were, in the past, were electrical utilities. Electrical utilities provided power to your house by stringing up electrical wires that led to a large generating plant that used coal or water power to produce electricity that was then wired to your house. And there was really no need for competition in this market because one utility taking care of the wires and the generation could provide all the power that a particular house or a particular market might want to buy. So we have a situation of natural monopoly. The alternative would be for another power company to come in, build a large power plant, and string their wires to your house so that you could then choose whose electricity you wanted to buy. As long as we think of power generation as coming from utilities that then send the power to your house through electrical wires, it really seems that it is a natural monopoly. We don't want a lot of firms out there stringing their own wires and building their own plants. Now we're going to talk more about electrical utilities a little bit later when we talk about the possibility that monopolies might be deregulated. But for now, let me summarize. The three things that create monopolies are, first of all, sole ownership of some strategic resources, as in the case of the Diamond Cartel. The second is government action, usually in the granting of patents or special licenses. And finally, natural monopolies, which occur when there are a lot of economies of scale in an industry, so that the point of efficient scale has a lot of production relative to demand in the market, when all the demand in the market can be met at very low cost or at diminishing cost by a single firm. Given that we have a monopoly, or supposing that we have a monopoly, how then will this monopoly behave? Will it charge high prices and sell little output, or will it charge lower prices and sell more output? In the next lesson, we take up the question then of the monopolist's problem, how to make the trade-off between higher prices and larger sales.